Hello everyone. Let's start the new unit, atomic structure. The first topic I am going to discuss in this unit is on atomic spectra. It was Isaac Newton who discovered that white light disperses into different colors when it is passed through a prism. He called these colors as spectrum. It was Newton who introduced the term spectrum. This discovery he made in 1666. It was the same year in which he discovered the laws of mechanics and the law of gravitation. That year was called, it's usually called the miraculous year of Newton, Newton's miraculous year. Here you can see two types of spectrum. On the top panel you can see different bands of colors, different patches of colors. This is called a continuous spectrum. Okay, one color fuses into the other color continuously, right? On the bottom panel you can see that there are emissions of colors at specific wavelengths. Okay, at one wavelength you have one color, violet here, then blue, then a light blue here, then green, then towards the right side red. Okay, in between there is a yellow orange color. Okay, so these colors are emitted at specific wavelengths. You can also see that on a dark background you have bright colors, you have bright lines. Now this is called a line spectrum because of its appearance. Okay, colors are emitted at different wavelengths. So they are separated, they are discontinuous. Okay, this is called a line spectrum. And in particular this type of a spectrum is called emission line spectrum. Okay, when you have a on a dark background, when you have bright colors, bright lines, it's called an emission line spectrum. Okay, so this is a classification, or you can distinguish between a continuous spectrum and a line spectrum. Okay, in 1802 a, an English chemist called William H. Wollaston, he made a discovery. He had contributions in different branches of science, in chemistry, in physics, and he made a discovery while studying the spectrum of sun, while studying the sunlight. Then he discovered that it is not a continuous spectrum. I mean, it's a continuous, there is a continuous background, but in this continuous background, in the visible part, for example, you can see dark lines. Okay, so this discovery was this dark lines in the solar spectrum. That discovery was first made by Wollaston in the year 1802. You can see here these dark lines in the solar spectrum. In the year 1814, Joseph von Fraunhofer systematically studied these dark lines in the solar spectrum. You can see here different classifications. The major lines are named, this naming was given by Fraunhofer: A, B, C, D, E, F, G, H, K. And the minor lines are given another classification. Okay, so he classified nearly 574 dark lines in the visible part of the solar spectrum in 1814. So this was the first systematic study of these dark lines in the solar spectrum. And these dark lines in the solar spectrum are today called Fraunhofer lines, named after him. Between 1850 and 1859, this duo, Gustav Kirchhoff and Robert Bunsen, you can see them here. The one standing is Kirchhoff, and the senior person sitting is Bunsen at that time. So these duo, they collaborated in the area of spectroscopy, and they made three important discoveries in spectroscopy. Okay, the first discovery was that the spectral lines in the atomic spectrum of an element occur at characteristic wavelengths of that element. Okay, it means that for example, you can see two spectrum here. The top one is the sodium spectrum. You can see that the characteristic spectral line of sodium is a yellow line. Actually, there are two yellow lines, two closely spaced yellow lines. If you use a prism with a relatively low resolving power, you will see only one, normally only one yellow line. If you use a diffraction grating of a larger resolving power, you will see two closely spaced D1 and D2, they are named. Two closely spaced yellow lines. So the average wavelength of these yellow lines is 589 nanometer. Okay, so here you can see a single yellow line at 589 nanometer. So the yellow line at 589 nanometer is a characteristic wavelength of sodium. Now below you can see the spectrum of mercury. Okay, you can see different lines, violet, blue, green, okay, yellow, green, then a yellow, faint yellow line also in different with specific wavelengths. Okay, so this is mercury spectrum. Now I have chosen sodium spectrum and mercury spectrum here because they are familiar to you from physics lab. You make different measurements using sodium and mercury. Okay, so the Kirchhoff and Bunsen discovered that for each element, so they measured the spectrum of different elements, and they found that the spectral lines occur at specific wavelengths for one element, and for the next element, these the positions of the spectral lines are different. So it's something like a signature, a fingerprint. As the spectrum, atomic spectrum is like a signature or fingerprint of the element. Okay, it's very unique. This was the first discovery. Now the second discovery was related to Fraunhofer lines. When they studied Fraunhofer lines, they found that in the case of many of the Fraunhofer lines, their wavelengths coincide with the characteristic wavelengths in the emission spectra of elements heated in the lab. Okay, so they have recorded emission spectra of different elements by heating these elements in using an arc lamp. So they have recorded these emission spectral lines. So the positions of these emissions wavelengths in these emission spectral lines in different elements, for example sodium, okay, or any such element, so they noticed that many of these lines in the Fraunhofer, many of the wavelengths in the Fraunhofer lines coincide with what they have produced in the characteristic wavelengths of different elements that they have produced in the lab. Before considering the third discovery, let us see how emission spectrum and absorption spectrum are produced. Okay, consider a hot source, a hot solid. We know that any hot condensed matter will emit all frequencies, like an approximate black body. Okay, black body is just an idealization of this hot body, hot condensed matter. So when light from this hot source is allowed to pass through a prism, what we get is a continuous spectrum, a continuous patch of colors. Now consider another situation. Take a pure element like pure mercury. Then it is heated on an arc lamp. At the time of Bunsen and Kirchhoff, they were using arc lamps. Nowadays we use a different technique. We use electric discharge to excite the gas. Okay, we will discuss that later. But let us look at this. We suppose a pure element is heated in an arc lamp. Then you get a vapor, a low density vapor of the element. When light from this low density gas is allowed to pass through a prism, what we get is an emission spectrum. On a dark background, we have bright lines, characteristic spectral lines of that element. So this is how we get an emission line spectrum. Now let us see how we can produce an absorption line spectrum. Take the same element, heat it, and let us keep the temperature of this low density vapor lower than the temperature of this hot source. This time the continuous light, the light of all possible wavelengths coming from this hot source is allowed to pass through this relatively low temperature gas. So this is the low density gas of the same element. So when a continuous light passes through this cooler gas, what happens is this element, the atoms of this element, okay, they absorb characteristic wavelengths from this incident light. So if the emergent light is allowed to pass through a prism, what we obtain is, on a bright background you have dark lines. This is called absorption line spectrum. How do we get a bright background? It is the continuous spectrum of this hot source. We know that the spectrum of the hot source is a continuous spectrum. That is the continuous spectrum that we obtain as the background. What are these dark lines? They are the characteristic spectral lines of this element. So for the same element, if you produce an emission line spectrum and an absorption line spectrum, Bunsen and Kirchhoff observed that the wavelengths of each bright line in the emission spectrum exactly coincides with the corresponding dark line in the absorption line spectrum. One-to-one correspondence between each bright line and each dark line. Okay, their wavelengths exactly matches. This was their third discovery. Okay, the spectral lines in the emission spectrum and absorption spectrum of the same element have exactly the same wavelength. Now with this discovery, they were able to explain why many of the Fraunhofer lines have the same wavelengths as that we see in the emission spectrum of different elements. Okay, the emission spectrum that we produce in the lab, of different elements that we produce in the lab. They explained this on 27th October 1859. Kirchhoff was presenting the results in a meeting of the Prussian Academy of Sciences in Berlin. And he explained that the core of the sun is emitting like a hot source. Okay, it's emitting continuous spectrum of, it's like a black body. Okay, though this idea of black body, we know that Kirchhoff himself produced introduced the idea of black body, but it was in 1 year later in 1860. So this hot source is emitting all possible frequencies. So the core of the sun is emitting all possible frequencies. When these light of all possible wavelengths, this composite light, when it passes through the outer layers of the sun, they are at lower temperatures. Then the atoms in the outer layers of the sun absorb their characteristic wavelengths from this composite light. So when sunlight reaches the earth, when we analyze it using prisms, what we observe is a continuous background, that is the continuous spectrum from the core of the sun, and on which you get different dark lines. So these dark lines are due to they are the characteristic spectral lines of elements, different elements present in the outer layers of the sun. Okay, now we see that many of them, these Fraunhofer lines, have the same wavelength as that of the the emission spectrum of different elements in the lab. So it means that these elements actually present in the outer layers of the sun. Okay, now this particular date, this particular presentation of Kirchhoff and Bunsen, okay, this is considered to be the birth of the area called astrophysics. Okay, where we are able to explain the internal composition of a star, which elements are present in the star, by analyzing the stellar spectrum. Okay, so this trend, this development was made by these two persons, Kirchhoff and Bunsen, by analyzing solar spectrum. Now let us come to hydrogen spectrum. Okay, what you see here is hydrogen spectrum in the visible region of electromagnetic spectrum. Okay, there are four prominent lines. Okay, there is a red line which is named as H alpha line. Okay,
Then the longest wavelength line is called H alpha line. Its wavelength is 656.3 nanometer. Then the next prominent line is a light blue line, H beta line, with the wavelength 486.1 nanometer. Then there is a blue line, H gamma, 434 nanometer. Then there is a violet line, H delta, for 10.2 nanometer. Okay, if you have very high resolution diffraction gratings, you can observe two more faint violet lines, but since their wavelengths are less than 400 nanometer, they are considered to be in the ultraviolet region. So there are four prominent lines in the visible region, but there are other fainter lines, okay, in the same visible region. These are the most prominent, I mean the highest intensity lines. Now the first person who measured a line in the visible region of hydrogen spectrum was Angstrom, Anders Jonas Angstrom. Okay, we are familiar with the name Angstrom because we use it as the as a unit for length. 10 raised to minus 10 meter is called Angstrom. So in 1853 it was Angstrom who measured the wavelength of H alpha line of atomic hydrogen spectrum. Okay, it was the highest, it's the highest intensity line, the brightest line in the visible part of hydrogen spectrum, H alpha line. So he measured it. Then some 2 decades later, okay, in 1881, William Huggins, okay, he was an astronomer, observational astronomer, and he measured some 10 lines in the visible region of hydrogen, okay, in this visible part of the hydrogen spectrum, and he measured it not in the lab but in solar spectrum. Okay, so the H alpha line was measured in the lab by Angstrom, but Huggins measured 10 different lines in the visible region of hydrogen in the solar spectrum. Okay, so these were the first 2 measurements of the hydrogen spectrum. Okay, in 1885, a mathematician called Johann Balmer, okay, in 1885 he was nearly 60. He analyzed the different wavelengths so far measured in the visible region of hydrogen spectrum, and he came up with a formula connecting the wavelengths of these spectral lines together. This is called Balmer's formula, and this is the formula. The wavelength in the visible region lambda is equal to some constant. This was called Balmer's constant earlier, 364.507 nanometer, into n square by n square minus 4. Okay, this much nanometer, where n is an integer greater than 2, 3, 4, 5, 6, etc. So if you put n equal to 3, you will get the wavelength of H alpha line. For n equal to 4, wavelength of H beta line, like that. Okay. So this is Balmer's formula. This corresponds to, this gives you the wavelengths of different spectral lines in the visible region of hydrogen spectrum. Okay. Some 3 years later, in 1888, Johannes Rydberg, okay, he generalized Balmer's formula. He got a more general formula which explains the spectral lines of all the spectral lines measured in different regions. At that time, both in visible region as well as in infrared region, spectral lines of hydrogen were recorded. So all these spectral lines could be explained using this formula. It's now called Rydberg formula. Okay, 1 by lambda equals R. R is a constant, Rydberg constant. Its value is 1.097 into 10 raised to 7 meter raised to minus 1. R into 1 by n1 square minus 1 by n2 square. n1 and n2 are integers with n2 greater than n1. Okay, so if you put let us say n1 equal to 1, then n2 will be 2, 3, 4, etc. When n1 equal to 2, n2 is 3, 4, 5, etc. Okay, now we can see that this we can show that Balmer's formula is a special case of Rydberg formula with n1 equal to 2 and n2 is equal to 3, 4, 5, etc. Okay, so with that you can with this idea you can obtain the relationship between Balmer's constant and Rydberg constant. Okay, you can connect them. So these were the empirical or the mathematical way of looking at the spectral lines. So we can see that there is some internal symmetry, there is some internal order for this randomly looking spectral lines in the in hydrogen spectrum. Okay.
Let us see an application of this recording hydrogen spectrum from the starlight. This is quite similar to the way Kirchhoff explained the presence of many spectral lines in solar spectrum, many Fraunhofer lines in solar spectrum. This is this telescope is called Hubble Space Telescope Imaging Spectrograph. Okay, STIS, Space Telescope Imaging Spectrograph. So here light from a star, this is a continuous light, okay, containing all wavelengths. When it is coming through to the telescope, okay, then on the way it passes through many clouds, okay, or the telescope is positioned in such a way that the starlight is allowed to pass through certain clouds that we want to study. So when it passes through each cloud, okay, one characteristic wavelength is absorbed, so we get a dark line. Another cloud makes another characteristic, it absorbs another characteristic wavelength. So it's not necessarily a single wavelength, but the idea is, overall procedure is something like this. So each cloud will absorb some characteristic wavelengths, not necessarily a single wavelength, but a group of wavelengths. So when you look at the final absorption spectrum recorded by this STIS, what you get is something like this. Okay, by analyzing this spectrum, we can get information about what type of elements are present in these interstellar clouds. Okay, even by looking at the Doppler shift of um, these spectral lines, we can analyze how far they are, I mean, what is their speed of recessional speed. And once you get the recessional speed using Hubble's law, you can calculate the distance of these clouds also, interstellar clouds also. Okay, so there are many information that we can gather by recording these spectra from the stars, okay, from different strategic positions. So this is uh, one way which currently we use spectroscopy in analyzing stellar spectrum. Now, aurora or northern lights is a phenomena in which um, spectra are produced in nature itself. These auroras are produced when streams of charged particles, particularly protons and electrons from the sun, collide with atoms in the upper atmosphere and excite them. Okay. Now in this different colors, this green hues are produced by oxygen, red hues are produced by both oxygen and nitrogen. So many colors are produced there. Generally, we observe these in the near to the in the regions near to North Pole. That's why they are called northern lights, aurora borealis. Okay, now we have discussed so far we have discussed many points related to atomic spectra. Now these points also raise many questions also. For example, why line spectrum? Okay, why atomic spectrum is a line spectrum? Why is it unique for an element? Why is there exact matching of emission and absorption lines? Okay, and why are there exact relations between these lines? We have seen that in Balmer's formula and Rydberg formula. we can write exact relations between spectral lines in a series, at least in the case of hydrogen. So these are open questions at that time, okay? And now to get the answer to these questions, we should consider the structure of the atom. We should consider how spectral lines are produced. Okay, not just how they are produced in the lab by heating an element on an arc lamp and passing the light from this hot gas through spectroscopy, not the methodology or experimental methodology, but what is happening at the atomic level. Okay, only then we can answer all these questions. So the answer is there in the atomic structure. So in the next class we will start with the structure of the different models related to the structure of the atom. In particular, we will look at Rutherford's atom model. Okay, before that we will look at Thomson's atom model, and then we will look at the Rutherford's atom model. On the figure, in the figure you can see the famous alpha particle scattering experiment designed by Rutherford. Okay, we will discuss it in detail in the next class. Thank you.